Hello, my name is Eric Peterson. I'm a postdoctoral researcher at the Geophysical Institute, and I study debris-covered glaciers. These are glaciers with an extensive rocky debris covering that changes the ice melt rate. For a thin debris covering, the darker surface absorbs more solar radiation and increases melt rates. But for a sufficiently thick debris cover, about several centimeters thick or more, the debris actually insulates the underlying ice and reduces melt rates. It's important to understand this process in great detail in order to model glacial change into a warming climate, in particular for regions like Alaska, the Himalaya, and mountain ranges around the world where debris-covered glaciers are common. To this end, I'm working on an NSF-funded project with Regina Hawk on the Kennicott Glacier near McCarthy, Alaska in the Wrangell Mountains. We went out last summer and installed an automatic weather station on the glacier surface to measure air temperature, incoming and outgoing radiation components, and wind speeds in order to constrain glacial melt models. We also installed melt stakes in the debris, basically allows us to come back various times and measure the surface lowering as a proxy for ice melt. We also take a detailed look at the heat flux through the debris cover. Now, this is the key component that makes the difference between a debris-covered glacier and a clean glacier in terms of its melt rate. And in order to do this, we measure temperature at differing levels in the debris layer and apply a heat conduction and conservation equation shown here in the middle. Now, I've developed a new way to look at this equation, at least in the glacial subfield, to separate out the degree of heat that's conducted entirely through the debris and is available for melt of underlying ice versus the amount of heat that's lost to various processes. And what processes might we lose heat through? Well, for example, the melt at the base of the debris causes meltwater, which can be wicked up through the debris, similar to a soil, and is then evaporated at the hot debris surface. And a little bit of evaporation goes a long way in terms of heat losses. And we see this average daily signal where we lose a lot of heat at midday, where we're also getting melt of glacier ice and hot debris surface. So this is really shedding light on one of the mechanisms by which debris can insulate the ice and reduce melt rates. This is a manuscript that I'm preparing to submit for publication towards the end of this summer. So I'll wrap up. Thank you for your attention. If you're interested in more on what we're doing on this glacier, scan this QR code for video content on YouTube. Thank you and enjoy the rest of the Arctic Open House.